Applications of the Bernoulli equation in these couple of problems. The first is we talked about the whole derivation that we went through over the past, I guess it was extended out to the past 2 weeks because the midterm was in the middle, is talking about having these three types of energy, right? Pressure energy, kinetic energy, and potential energy. Pressure energy, we said, was pressure divided by gamma, the specific weight of our fluid. Kinetic energy was V squared over 2G. And potential energy, we said, was just Z, some elevation above a datum. Now, all of these are presently being expressed as heads, which is to say that they're all lengths, right? So if you had worked out the units or the dimensions for these, they would all come out to be lengths in this case, the way I have them written. And so the power of the Bernoulli equation really comes in writing this long form. So let me write it out real quick and then let's talk it through. P1 over gamma, so the pressure energy at 1 plus the kinetic energy at 1, sorry. I wanted that square to be up there. This should be a 1 though, divided by 2G plus Z1, the potential energy at 1. The sum of those being equal to the sum of energy at point number 2, so P2 over gamma plus V2 squared over 2G plus Z2, okay? So all we're really going for in a lot of these problems that we're going to work through is finding first opportune places to identify some of these locations. So for example, P in the atmosphere is basically equal to 0 because we're working in gauge pressures here. Okay, so relative to atmospheric pressure, the pressure in our system, when you have an opening, so a jet out of the end of a pipe or something like that, that will give us one term, hopefully, that we can cancel out. So that's one place that we look for some convenient location to identify here. We often have either Z1 or Z2 being equal to 0, which is to say that we just choose one of those to be our datum. So relative to the other one, it's 0, right? So if we know some dimension, how different Z's are from each other, that will be helpful. And then finally, we might be given one of the two velocities. There are cases that we'll talk about today where particularly in front of the stagnation pipe, we would have a 0 velocity, and so that's a key place to put one of our locations of assessing the energy equation, this Bernoulli equation. All right, so I just want to quickly go over the last 3 slides that we had in class last week, which look like this. So this is kind of a typical pipe. We have what's called a static pressure tube over here. So this static pressure tube is this guy. You can see that it's just a tube coming into the top of a pipe in this case. Flow is going from left to right. We do have active moving water, so we're moving beyond hydrostatics now to really look at how energy is changing through any flowing system. Now in our case, we're not accounting for any energy losses at the moment. So we are assuming that we have frictionless flow, and we don't have any other losses. Like for example, you can't really put this pipe down into this opening down into a pipe without having probably some loss around it. Just the fluid having to hit it and come around it and all that. There's going to be some loss associated with that. We're going to ignore that for now. Okay, so we're really just looking at how energy changes forms. So among the three, so kinetic, pressure, and potential energy, how those are changing from one place to another. So that's all we're doing, is that the sum on each side of the equation has to be equal. And we'll manipulate that to solve some important problems. Let's see if I can move that out of the way. All right, and then the second side of this is the stagnation pressure, where pressure tube, where we expect that right here, V2 is equal to 0. Okay, so this is a key place where we would apply the Bernoulli equation to have one of our terms go to 0. We still have this full sort of recognition of our Z and this pressure that's built up inside of this tube that's represented in the system that we do. So just a reminder then, when we apply a static tube measurement, we're basically, if we look at applying the Bernoulli equation from location number 1 to location number 4, then essentially this reduces to P plus gamma times Z. That's going to be some constant, and what that ends up really coming down to is H is equal to P over gamma, the height of rise inside of that tube. Okay, and if we assume that Z is equal to 0 here, then this second term in that equation goes away. But in any event, the height of rise inside that tube is directly proportional to the pressure energy at this location. All right. When it comes to the stagnation tube, a little bit different. Now the height of rise here, capital H, is now equal to two pieces of energy here, the pressure head as well as the velocity head. Okay, so actually this was, sorry, I guess I kind of goofed this up a little bit. This probably should have been, no, that's right. This is V1 squared over 2G is the velocity away from the opening here. So that's somewhere upstream. And P1 is also the pressure head that's further upstream as well. Okay, so our static and velocity heads essentially add up here, and both of these add up to the this total rise that we have inside of a stagnation tube. All right, okay. So let's start with a situation like this. We have a pipe, water is moving from left to right. That's kind of obvious here. And we have a pressure static tube on the left-hand side here. And then on the right-hand side, after we go through a constriction, so this total Q, whatever flow rate is coming through here, is now having to move faster and faster as it goes, as the size of the pipe winnows down. And then we get to point number 2 here. Okay, so what we're going to do, so the question here is water flows through a pipe contraction as shown in the figure below for a given 0.21 meter difference in the manometer levels, determine the flow rate. So this H1 and H2, the difference between those is 0.21. So you can expect that somewhere along the way, we're going to be able to relate H1 to H2, but they're both unknown to us at the moment. So that's one piece of this. The other piece of this is determine the flow rate. So remember that Q in general is equal to V times A. And if I make this specific for point number 1 right here, Q1 is equal to A1 times V1, or V1 times A1, as I have it written. But we also note Q2, of course, is also equal to V times A, in this case, V2 times A2, right? And for all of the flow that comes in from the left and goes out the right, we also have to say that Q1 is equal to Q2. Those two things have to be equal to each other because we can't store this water, in this case, coming through anywhere, all right? Okay, but then we also have our Bernoulli equation. I'm going to write out the equation, and then we'll talk a little bit about strategy here. So P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. Okay, now we have 6 terms here, and this can look a little bit daunting, but the whole reason that we think about trying to be really strategic about this is that we can often simplify this to solve for something valuable. In this case, we either want V1 or V2. We don't necessarily need them both. We really just need one of them or the other, all right? The other thing that we can point out is if our datum here is this location, the center of our the center line of this pipe, then both point 1 and point 2 lie on that datum, and the z's will go away. So Z1 is equal to Z2, and because they are on both sides of the equation, Z1 is over here and Z2 is over here, they will cancel out, right? Whatever they are above, I don't know, the ground in the room that this is set up in, or sea level for that matter. They will be the exact same number, so we can cancel those out. So the same potential energy exists at point one as there is at point two. It's not that they're zero, it's that they're equal to each other, okay? So what about our pressure and velocities? All right, we know that V2, because we put our second point right in front of the stagnation tube, we say that V2 is equal to zero. Okay, so that simplifies our life by basically making this equal to zero. Now we have an expression where we can simplify this to say P1 over gamma plus V1 squared over 2G, or the pressure head at 1 plus the velocity head at 1 is equal to the pressure head at 2. So one thing that I want to point out is, before we even go any further, is that we're talking about taking two kinds of energy on the left-hand side, two flavors if you want, pressure head and a velocity head, and converting it completely to the pressure head on the right-hand side, okay, at point two. So this is kind of the advantage of using Bernoulli for us. Now, the other thing I want to point out, we'll go to the next slide and I'll write this out a little more, but remember, pressure can be written as gamma times H as well, okay? And that, in fact, P1, so if we institute this, P1, for example, is equal to gamma times H1, right? We can also then say that P2 is equal to gamma times H2. So we don't know what those values are, but we can plug both of these representations for pressure into the Bernoulli equation to eventually figure out this, H2 minus H1 for this 0.21 that will help inform the problem here. Okay, so I realize this all looks daunting, but we haven't solved for anything just yet, but we have simplified our lives, and we have done this with basically three equations. One was continuity up here, the second one is the Bernoulli equation, and then a bunch of assumptions that go along with it to simplify that, and then the third was basically the hydrostatic pressure relationship that we are familiar with from several weeks ago, beginning of this class. Okay, I'm going to go to the next slide now, where we just kind of have a blank canvas to work. I do have a small version of this image for us to reference, but now we'll be able to work through this a little better. So we started with, I'm just going to rewrite the Bernoulli simplified version here, P1 over gamma plus V1 squared over 2G is equal to P2 over gamma. And we said that P1 was equal to H1 gamma, and that that's supposed to be a semicolon. P2 is equal to H2 times gamma. So let's plug those in here. So H1 gamma over gamma plus V1 squared over 2G is equal to H2 times gamma over gamma. Okay, so right away, you're looking at this going, oh, this simplifies quite a bit, right? We can get rid of some gammas, just like that. And now we've got something more like V1, oops, let me move it over here a little bit. V1 squared over 2G is equal to H2 minus H1. So all I did was subtract H1 from both sides, right? And that is exactly what 0.21 meters is, okay? So we can now solve for V1 squared is equal to 2G times this difference, H2 minus H1. And when we do that, V1, okay, so this is 2. We are working in meters, so we're going to multiply by 9.81 meters per second squared, and then we multiply by 0.21 meters, which is given in the diagram as H2 minus H1. the difference between those. So when we work this out numerically, we get that V1 is the square root of 4.12 meters squared per second squared, and that comes out to be 2.03 meters per second. Okay? All right, so we've got V1. That's useful to us because now we can calculate Q1 as being equal to V1 times A1. And we hadn't calculated A1, but we were given a diameter of 0.13 meters, right? So we can calculate A1, and we now have V1 from using the Bernoulli equation above. Okay, so this is now 2.03 meters per second. And then we've got the area of a circle here for our pipe, which would be pi over 4. And then we multiply by the diameter squared here, so 0.13 meters. And we're going to square that. And that comes out to be a pretty small flow, 0.0269 cubic meters per second. Okay, we can write that in scientific notation, but essentially we have two significant figures there. As I look at what we were given, we've got two significant figures, so probably rounding to 0.027 would be the smart thing here. But in any event, that more importantly for the mechanics of how we related the continuity equation with respect to just mass balance, and then the energy balance that is manifest in the Bernoulli equation, plus our hydrostatic relationship. Putting all three of those together helped us come up with this from only two numbers, I guess, that were given in this situation. All right, any questions on this?
We have, sorry. So does Q2 equal 0 since V2 equals 0? If so, how come Q1 equals Q2?
Good point. So, right, I was a little bit loose with this. This V2 should actually be the velocity, the mean velocity going around. This V2 was meant to be 0. So I probably, in other context, we will see this. I was a little too loose with that. So thanks for asking about that. Let's call this V2 prime or something like that, to note that would be the average around the stagnation tube. Yeah, thanks. So Q2 shouldn't be 0, but there is no flow right at the front of that stagnation tube. Good question.
I think that's it for now.
Okay. Terrific. Glad you asked. Okay. All right, here's a mystery fluid in a tank. We have a tank here. You can see it's filled with a combination of air and liquid, and it's pressurized. Then in the bottom of it, it has this tube coming out, and it shoots out into the world at a velocity of 40 feet per second, okay? So we are going to, so the question is, an inviscid incompressible liquid flows steadily from a large pressurized tank shown in the figure here. The velocity at the exit is 40 feet per second. Determine the specific gravity of the liquid in the tank. Now remember, of course, SG is equal to, I'm going to write this in terms of gamma, but gamma of our mystery fluid divided by the gamma of water, right? And so if it's 1, it's the same as water. If it's greater than 1, it's heavier than water or more dense than water. And if it's less than 1, it is less dense than water. Okay, so the reason I wrote this in terms of gammas, remember that we have some gammas in our Bernoulli equation. So that's going to come to our rescue here pretty soon. I'll write out the Bernoulli equation. P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. I think a reasonable question on the next exam would be, well, it'd be better if you could fill it in, but it might be if you were kidnapped and someone gave a video of you and you wanted to indicate that things weren't okay, you could always throw out the wrong version of the Bernoulli equation, because we will write this so many times you will get tired of hearing it from me, but it'll hopefully get kind of tattooed on your brain in the same way it's tattooed on mine. But in any event, okay, so there's our equation. We have, let's identify the top of the liquid as location number 1. And the reason I did that is that I have a known pressure here that I can apply to that location. And it's a place where things are going to be moving pretty slowly. In other words, we're going to assume that the velocity at point number 1 is 0. The fluid, there's a continuum, of course, of all of the liquid molecules in touch with each other, but there's this indication of being a large pressurized tank, which means that the level isn't falling very fast, even though we have a very fast rate of flow out the bottom. We don't know anything about the diameter at the moment, so we don't know the actual flow rate. We just know that it's moving at a very high velocity of 40 feet per second, all right? Location number 2, I'm going to put right here at the exit to this pipe. And the reason that I'm going to do that is, 1, we're given a V2 here, right? So V2, we have, I'm just going to say equals V2. The other thing that simplification that we talked about last Thursday applies here as well, that P2 is also equal to 0 because this is jetting out to the atmosphere. Okay, so so we also said earlier, I didn't write it in, but basically that V1 is equal to 0. Okay, so now if we take the master equation here, this is going to go to 0. We said that P2 is 0, and we know that, and we know what V2 is. I'm just going to check that. Okay, so we know V2. We also know that if we set up Z equals 0 right here, then I know what my Z1 is. It's 10 feet plus 5 feet, right? So the other reason to use the top of that liquid air interface inside the tank is that we know something about Z at that location, okay? So Z2 will be equal to 0, but Z1 will be equal to 15 feet. Okay, so if I look at my equation now, the other thing that I know is I'm basically given a P1, right? That P1 is this 10 PSI. That's the pressure that's coming down on top of the liquid before we even move down into it. And we know Z2, or Z1 we said was, shoot, I didn't mean to cross that out. But anyway, we said this was 15 feet, and we said that Z2 is 0. So we've simplified this once again, and I'll rewrite it because it's, quite frankly, a little hard to understand exactly what we've done at this point. So let's do that. We now have 10 pounds per inch squared. Oh boy, we're acting up early today. All right, that's supposed to be inch squared divided by gamma plus 15 feet is equal to V2 squared, which we said we know from the problem is 40 feet per second, and that whole quantity squared divided by 2 times G. Now G, because we're working in English units, is 32.2 feet per second squared, right? Okay. Okay, so we basically have an expression where we could solve for gamma, right? Algebraically, we can work through and solve this for gamma. The one thing that I want to point out before we do that, though, is that now we're taking what's left after all of our zeros. We have a pressure energy and a potential energy on the left-hand side, and we're transforming that to a kinetic energy on the right-hand side at point number 2, okay, which is kind of cool that we're just looking at these energy transformations. All right, so on the next slide, I'm going to go ahead and work the algebra to basically figure out gamma here. We don't know that it's water. It may not be. In fact, I'll just give away that it is not water, but let's figure out what our gamma is so that we can figure out our specific gravity, which was the question here. Okay, so I'm going to rewrite this because I need to make a transformation here. We had 10 pounds per inch squared. We're going to multiply that by 144 inches per square foot, square inches, pardon me, per foot squared, so that we get that in the denominator because everything else is in feet. Remember, this is still divided by gamma. We add the 15 feet of elevation difference that we have between point 1 and point 2, and that is equal to this 40 feet per second quantity squared divided by 2 times our acceleration due to gravity, 32.2. Ooh, that's a terrible 2. How about that? Feet per second squared. Okay, so now we can rearrange this. This comes out to be 1,440 up there. So we end up with, why don't I just go ahead and put 14, I'll take one more step here, 1,440 pounds per foot squared divided by gamma is equal to 24.84 feet. And then I'm moving that 15 over here, minus 15 feet, right? So now we get gamma is equal to 1,440 pounds per foot squared divided by 9.84 feet. And that comes out to be 146.34 pounds per foot cubed. And if we compare that with that of water, so in other words, recall SG is equal to gamma over gamma water, and in English units, our specific weight of water, so this is 146.34 pounds per foot cubed. But for water, it's 62.4, pardon me, pounds per foot cubed. So this comes out to be a ratio of 2.34. Okay? So there's our specific gravity. So this fluid that's moving at 40 feet per second is actually twice as dense as water, more than twice as dense. 2.34 times as dense. And let's see, I didn't look carefully at my significant figures, but if I did, it looks like I would come down to just going with 2 in this case, right? It looks like we have one significant figure for the 5, the 10, and the 40 that are given there, plus the 10 psi. So a bunch of our constants here, our inputs are one significant figure. All right? Okay, any questions on that one? So hopefully you're getting the pattern of kind of taking what we know about things like continuity, in other words, the mass balance with Q, and the energy balance with Bernoulli's equation to kind of put all these together. We good, Emma?
Yeah, we're good.
Okay. All right, problem number 3. Can we find the diameter of a pipe? Okay, so an unknown diameter here, D, is given. We are given the diameter back here as 1.5 inches. So the question basically is, water flows steadily through with negligible viscous effects through a pipe shown in the figure below. Determine the diameter D of the pipe at the outlet, which is a free jet, if the velocity there is 22 feet per second. Okay, so automatically you can guess, I'm going to put position number 2 right here, right? So we can call this V2 as a matter of fact. V2 is equal to 22 feet per second. We don't know what the cross-sectional area is upstream of it, right in this pipe. But we do know somewhere back here what the cross-sectional area ought to be. We just don't know the velocity there. So in this case, Q1 is going to equal Q2. Oh. And therefore, we can say that A1 V1 is equal to A2 V2, and we're given V2. If we can find a way to figure out, A2 or even V1 for that matter, we still don't need the area. We ultimately need the diameter, right? So we'll have to go back through our geometry to figure out the diameter. Okay, but there's position number 2 where I'm going to apply the Bernoulli equation. Where should I put location number 1? It looks like for starters, we probably want to do it somewhere in this pipe that is 1.5 inches in diameter so that we know that. I'm going to go ahead and just put it right here. And the reason I did that is because we have our standpipe here, which should be giving us some indication of the pressure head at that location. All right. So the flow that's coming by here is not really changing until it comes into some change in diameter. But in any event, I could put 0.1 number there. So P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. Okay, so once again, because of the configuration of our system, I can call this Z equals 0 right here, right, as my datum. And if I do that, then Z1 goes to 0, right? I've been given V2, so I'm just going to put a check mark there. We can figure out that value if we want. We'll get to that. We also note that the difference in elevation from this center of the bottom pipe to the center of the top horizontal pipe is 10 feet. So Z2 is equal to 10 feet compared to Z1 being 0. So we know that. And then the pressure at 2, because it's a free jet, we know goes to 0. So P2 is equal to 0. Oh, goodness sakes, is equal to 0. So the pressure at point 1, though, should be related to this 15 feet somehow, right? So we do have some information on the pressure head at that location. So I'm just going to check this. We don't know it directly, but we should be able to figure it out, all right? Okay. So let me write in, I want to simplify this, but I want to do it on the next slide. And when I do that, I guess I'll also note that there as well. Okay, I think I'm ready to slide over to the next slide. Are we okay with that? Is everybody caught up? Yeah, okay. All right.
So just to clarify, anytime there's a free jet, that means that your atmospheric pressure is 0?
Yeah, you're going to be at atmospheric pressure. So the Bernoulli equation, we largely work with gauge pressures. So yeah, that's part of the reason we choose that free jet location is because we can make the pressure 0 at that point. Yep. Okay, so let me rewrite this now with the things that are left. So we've got P1 over gamma plus V1 squared over 2G is equal to V2 squared over 2G plus Z2. So one thing I just want to point out, if we just talk about the transformations of energy, look at what we've done. We are going to we go from a pressure energy at point 1 plus the kinematic or kinetic or velocity energy at point number 1 to some combination of the kinetic or velocity head at point number 2 plus the potential energy there. So the pressure energy is gone, right? So we've had some transformations here, and both these sums on both sides of the equal sign, of course, have to add up to the same amount. Okay, so let's the other equation I want to write here is that P1 can be written as gamma times 15 feet, right? From the static tube equation that we talked about before, this 15 feet tells us about the pressure right there at number one. Let me draw in my number 1 and 2 again. And so we can plug that in directly, right? So if we simplify this, then we have gamma times 15 feet divided by gamma plus, and then V1, we don't know yet. So this is going to be V1 squared over 2G is equal to, now we have V2, so this is 22 feet per second quantity squared divided by 2G. I'm going to leave it at that for now and not substitute all those in. And then we add the 10-foot difference that we had between the elevations of point 1 and point 2. Okay? So note that we can cancel out those two gammas because they're in the numerator and denominator of the same term. So now I'm going to take a shot at, we've got 15 feet over here on the left. I'm going to move that over to the right, and I want to work out these to all be come down into lengths. So we're going to have V1 squared over 2G is equal to, this whole thing becomes 7.51 feet plus the 10 feet that we have from the Z2, and then minus the 15 feet we had on the left-hand side, okay? So if we work this out, we get 17.51 minus 15. That gives us 2.51 feet, okay? So I guess the one thing I didn't write out here is G is obviously 32.2. We'll write that out now. So V1 squared is equal to 32.2 feet per second squared times times 2. I forgot my 2 in the front there. And then times 2.51 feet. And that comes out to a value of 161.64 feet squared per second squared. So if I take the square root of that, I end up with 12.7 feet per second. Okay. Well, I did not give myself another slide for this, so that's okay. The last bit of this is fairly straightforward. Okay, so now we have a V1. We should be able to calculate a Q1, right? So we said that, let me just put up a little barrier there. We said that Q1 is equal to Q2, so V1, A1 is equal to V2, A2, and we know V1 and V2 now. So we can basically, should be able to rearrange this to solve for A. What I'm gonna do instead is plug in all the values that we know and leave this in terms of, I think it's D1 on the right, the left-hand side of this. So on the left-hand side, we have 12.7 feet per second times pi over 4, and then our diameter here, D, we don't know. This is the upstream one. We know that is 1.5, and then I'm going to just divide by 12 right here because it's inches. So that would give us feet, and we take that and we square it, all right? And then that is equal to our velocity, 22 feet per second. Oops, I forgot my T in there. Feet per second times pi over 4 times D2 squared. Okay. And so I'm going to skip the rest of the arithmetic to figure this out, but ultimately D2 comes out to be 0.0951 feet, which, if we convert that to inches, turns out to be 1.14 inches. Okay? Now, again, let's see, I did not, it looks like everything except that 10 is in two sig figs. So if we took the 10, I mean, I guess that would boil down to 1 inch diameter, right? At the end there. Questions, Emma?
Good.
No? Okay. Terrific. All right. At this point, this is perfect. I have 2 clicker questions for us. So let me go to it, and then. All right. So this goes back to these problems we were just talking about a moment ago. When a fluid is flowing, the static pressure is given as A, the pressure of the fluid measured when it's brought to rest, B, undefined until the fluid is static and not moving, C, the pressure measured by an instrument moving along with the fluid, or D, the hydrostatic pressure of the fluid. All right, so go ahead and take another 30 seconds to work on that. I actually had these queued up for the other day. But we didn't get this far. All right, got 64 respondents, 72, 73. How many more are you? Give you a couple more seconds. We're at a minute 3. 75. Going once. Okay, we'll stop there. Let's take a look at the results. Okay, the answers are pretty split up here. So 21 for A, 12 for B, 12 for C, and D 31. D got 31 votes. It's actually technically it turns out this is C, which is not a great question. What's the right way to put this? A great interpretation, in my view. I don't mind this hydrostatic pressure bit, except that here's part of the problem with that, though, is that you could have a pressurized system, and the hydrostatic pressure is reflected in having a manometer come out. But if you don't have that static tube coming up, then you don't necessarily know what your static pressure is, and a pressurized system could have a lot of different pressures at places. So the hydrostatic pressure doesn't quite work. D is wrong only because if you had 6-inch diameter pipe, the pressure that you can put in there is way more than that 6 inches of hydrostatic pressure. But hydrostatic is what we use to figure out if we were to put a stand tube at the top of it, a static tube. So that's not necessarily. I can see where you might want to choose 10, but remember, or D, pardon me. But remember that we're not actually working with the hydrostatics of just the cross section. Let's see, the pressure in the fluid measured when it is brought to rest. That doesn't quite work because if you brought all of the fluid to rest, you're no longer pressurizing the system, most likely. And therefore, it wouldn't stack up to the hydrostatic pressure. And then undefined until the fluid is static or not moving is kind of the same as A, more or less. So ultimately, that comes back to C, which I realize is not very fulfilling. But that ends up being the right answer, perhaps by process of elimination. So not perfect, but okay. Let's go to one more. I've got one more queued up here now about what is dynamic pressure. So let me get rid of that. New one here. Okay, so the dynamic pressure for a fluid is A, pressure when the fluid is moving, B, pressure due to velocity in the fluid, C, the pressure measured when the fluid is brought to rest, or D, the pressure due to the pressure head, velocity head, and elevation head. So is dynamic pressure all of those things, all of the energies, or those pressures, or is it one of these other 3 as identified, A through C? we doing here? We're up to 65, 66. It looks like we topped out at 75 a moment ago. So let's see if we get there again. Okay, I think, we're at 76 this time. About the dynamic component of this. Okay, we're at 1 minute. I'll give you guys another 8 seconds here. We'll go to 110 just in case anybody wants to change their answer here. All right, up to 77. Okay, good. All right, let's take a look at the answers. So they were split mostly between B and D. We had 11 folks put in A. So while it's this is actually, I suppose A is sort of accurate. The actual answer is B, and you can't be moving if you don't have velocity. So fair enough. It's kind of hard to have B without A, but it really is this pressure due to the velocity of the fluid. So the dynamic pressure is just that velocity head component. Expressed as a pressure, so not divided by gamma in that case. So B was correct here for those of you who chose that. D, I didn't realize I had that interactive feature. I just pressed on that and I got the right thing there. D, let's see, the pressure head due to pressure. So all three of them together is not an unreasonable expectation because you're putting all of those together. In this case, the dynamic pressure just works out to be the velocity component of those pressures. So, FYI. All right, terrific. Thanks for those. All right, so we're almost. We are right at time. I'm going to keep going through this last problem so that it's provided for you on on Canvas as a recording. You don't have to necessarily stick around for it though, but I'm happy to take questions afterwards. So I'm going to work through it, and if you guys leave, that's okay. You'll have it to look at later. But I had it queued up, and I wanted to make sure I went through it all the way. Okay, so if you have to go, I'll see you in class tomorrow. If you're going to stick around, I'll see you whenever this problem is done. It should only take me about 45 minutes. I'm just kidding. It'll take less than that. Okay, so oil flows through this pipe right here, and we have a U-tube manometer setup, right? So it's a closed manometer coming in on this side right here and in right here. Now, as you can imagine, we are going to identify this location as one, the upstream location, right in front of this stagnation tube. And then number two, I'm going to put over here right near this, basically what looks like a standpipe. So the two pressures that are experienced here are providing this offset in the manometer. All right, so it's 5 feet from this elevation down to this elevation to this pipe, and then we're going to call this H, the height of rise on for the manometry fluid. You can see here it has a specific gravity of 2.5, so it's 2.5 times more dense than water. Eventually, we will get to thinking about what happens if H is 0.7, but first we're going to work through some relationships to kind of figure this out first. So oil flows through the system shown in the figure below with negligible losses. Determine the flow rate. So we're going to use Q is equal to V times A. Get rid of that as best I can. So, of course, we could do that at 1. Q1 is equal to O, A1, V1, with the exception, of course, that this is going to be the prime. We're going to make our V1 equal to 0. So let's go ahead and just convert these all to 2 instead and focus on figuring out the velocity at 2. We'll get rid of that prime now. And somehow we will figure out how to use the Bernoulli equation to solve for the velocity at 2 to figure out this flow. We're given this area 2 at that location and area 1 at this location. And so you can see that the velocity at point number 1 going around the stagnation tube must be about half the velocity that we have at this narrower part of the system because the area halves, right? Oh, I guess it's a little more than halves, right? It's 24 square inches instead of 50 square inches. So so almost a factor of 2 difference there. All right, so we're going to use Bernoulli equation. The other equation that we're going to use is our old friend, the manometry equation, right? We're going to start from P1. We can go through this system and sort of look at all of these changes so that we can identify or come up with a relationship between the pressure at 1 and the pressure at 2, right? So we're going to use, this is continuity. We're going to use manometer equation. I'm just going to write it out because we'll actually do the math here in a moment. And then thirdly, we'll do energy, which is the Bernoulli equation. So let's go ahead. Actually, from manometer, let's go ahead and write it out. From P1, I can start with P1 and add some length here. By the way, I'm going to assume that this downspout here doesn't really have a lot of length to it. Okay. In other words, that I'm more or less kind of, it's infinitesimally small, and my stagnation could basically come out to just doesn't have to hook down that far. So this distance I'm going to call L1 from here to here. Okay. And this distance here is going to be L2. And I'm going to start by writing all of these relationships with L1 and L2, and then we'll plug in H being 0.7 to work this out. Okay, so P1, now if I'm going down in elevation, then I'm adding the pressure above me. So then I'm going to have L1 times gamma oil, right? And then that gets me to here. I work over to the other side. I go up, so I decrease my pressure. So I'm going to subtract H times gamma of the manometer, right? Now we have that pink fluid instead of the white. And then if we go up to the location to get me up equivalent with the elevation at point number 2, I have, I'm going to subtract again. Now I've got an L2 length multiplied by gamma of the oil, okay? And that essentially equals P2. Okay, so there's manometry, as we've done before. So that's a relationship we'll work with here to relate everything to H. And then maybe we should do that. Let me think, as I think about this here. Why don't we, I was going to rearrange that, wasn't I? Nope. We'll leave this as it is. What we can do, though, yeah, we'll do that when we get to it. Okay, so the last thing then, before we start working on this in earnest, P1 over gamma oil plus V1 squared over 2G plus Z1 is equal to P2 over gamma oil plus V2 squared over 2G plus Z2. Now, in this case, again, we can set this as Z equals 0 so that Z1 is going to be ignored. Okay, so that's essentially, where's my simplification here? That's going to go to 0. We also know then that the height difference here is 5 feet. So Z2 is going to go to 5 feet. So there's something we know. We also know that V1, because we put it right in front of our stagnation tube, is going to go to 0 as well. Okay. So we've simplified this a little bit. We've gotten rid of 2 terms on the left-hand side. We still have 2 terms on the right-hand side that we have to deal with, okay, plus the constant of 5 feet. So let's do that on the next slide. I'll give you guys a second just to make sure we're all at the same place. Okay. So now I'm going to rewrite this as P1 over gamma oil is equal to P2 over gamma oil plus V2 squared over 2G plus 5 feet. And that could be rewritten, it's just moving that P2 to the right-hand side. So P1 minus P2 over gamma oil is equal to V2 squared over 2G plus 5 feet. Okay, so we're still solving for V2 ultimately because we're being asked about the flow rate here. But we've got some other unknowns, which you're probably concerned about. We don't know P1, we don't know P2. We do know the specific gravity of the oil, so we could figure out gamma oil. But for now, this just feels like one equation with three unknowns. So to allay that fear a little bit, let's go back to our manometry equation. And from the manometry equation, I'm now going to bring that real quick. I'm going to bring P2 onto the left-hand side, and then I'm going to divide through by gamma oil to sort of from this equation, all right? And as you'll expect, that sort of helps us with this term in the Bernoulli equation. So now I have P1 minus P2 over gamma oil is equal to basically minus L1 plus H times the manometer specific weight divided by the specific weight of oil, and then plus L2. And now let me just rearrange this a little bit. This, I think, is just a little bit easier to think about. L2 minus L1 plus H times gamma manometer divided by gamma oil. And the reason I did that was just that, you know, this was L2, remember, and this was L1 right here, right? Those two lengths. So the difference between those, we still don't know them. So how have I made this easier for us? I haven't. Now I've made four. We have four unknowns. We don't know the P's on the left and we don't know the L's on the right. All right, but I promise we're getting there. What we're going to do now is substitute this term in for P1 minus P2 over gamma oil to try to make this a little more succinct. So if we do that, the other thing to note here, where did that come from? I have it in my notes. I know I figured this out. L1, I have L1 plus 5 feet. From I was very keen about this. I just wrote this out like an hour ago. Okay, L1 plus 5 feet is equal to L2 plus H. That doesn't help with, where did that one come from? I know what it is. Yeah, sorry. Okay, the other thing to note is that this 5 feet plus L1 is equal to this total length on the right-hand side, H plus L2. That's what it is. Okay, so from, I don't know, layout, we know that 5 feet plus L1 is equal to H plus L2, okay? And I can rearrange that now because I have this as L2 minus L1 right here. I'm just going to rearrange that to solve this in terms of L2 minus L1. So L2 minus L1 is equal to 5 feet minus H, okay? And the reason I did that is that now this is just from the layout. So I can now plug this into here and get rid of L1 and L2 and just have this in terms of H, okay? And then we can plug that back into our equation here, which is the Bernoulli equation. I think I gave myself another slide to do that with. So let me put all that together on the next slide, if that's all right. Okay. So we have P1 minus P2 over gamma oil is equal to 5 feet minus h. So that was from L2 minus L1, and then plus h times gamma m over gamma oil. Remember, that is this is basically our manometer equation. Okay. Then we can take this and set it equal to basically 5 feet. The two h's will cancel, right? We're adding one and we're subtracting one. So these two guys go away. So now we have 5 feet plus. Oh, I'm sorry. No, we can't do that. What am I thinking? Oh, I wish I could get rid of those. Sorry, can't get rid of those. I thought I was being clever, but I am going to put them together. So now I'm going to say h times gamma m over gamma oil. And I have a plus one, but I think it's supposed to be a minus one here. Right there. Okay? So that made it a little simpler. Now, we don't care about those p's anymore. We have them in terms of h. So now we can go back to the Bernoulli equation and substitute in this term for that P1 minus P2 term that we had there, okay? So on the previous slide, we had this guy right here. We're now going to plug in something in terms of H there. And then this is why I didn't plug in the 0.7 yet. You can now see where if we, regardless of what this height is, we can kind of work out this relationship. Okay, so now from Bernoulli, let me put right back to Bernoulli, or BE for the Bernoulli equation. We now have V2 squared over 2G is equal to, we said P1 minus P2 over gamma oil minus 5 feet. And if we now substitute this in right there, we get 5 feet plus H times the manometry fluid specific weight divided by the specific weight of water, or sorry, oil in this case, minus 1, and then plus, or no, minus 5 feet. Yep, minus another 5 feet. Now we get to cancel these 5 feet. They cancel out, right? A plus and a minus. So V1 squared, or V2 squared rather, squared over 2G is equal to gamma M divided by gamma oil minus 1 times H. Okay? And we know everything in here except V2. Right? Now, recall that we said in the problem statement, H is equal to 0.7 meters. Let me just make sure I'm right about that. Yeah. Oh, sorry, feet. Oh, we're working in feet. My bad. So this is feet. Okay, so V2 is equal to, well, V2 squared is equal to 2.5 divided by, and the specific gravity of the oil, 0.82 minus 1. I use the specific gravities, by the way. It will end up being the same ratio. I'm not working out the whole specific weight because it'll just be the same ratio here. And then times 0.7 feet. That comes out to, I don't have a number for that, but, whoops, I forgot to multiply by, hang on, got to multiply by 2, and 32.2 feet per second squared as our acceleration due to gravity. So V2 comes out to be the square root of 92.36 feet squared per second squared. which comes out to be 9.61 feet per second. Okay? We still haven't figured out Q, but now we have a velocity. We have the velocity at 2. Okay? So now, I think I've run out of room here, so we'll just do this kind of, let me move this guy over. Do this over here. So now Q2 is equal to A2 times V2. We are given that A2 is 24 inches squared. So we're going to convert that to feet because this is in feet per second. So we'll multiply by 1 over 144. So 1 foot square per 144 inches squared. And then multiply by 9.61 feet per second. And gosh, that came out as a straight line. But anyway, this quantity comes out to be 1.60 feet cubed per second, or CFS. I didn't check my units, or looks like we're given a 5 here. So I guess that comes out to be 2 cubic feet per second with significant figures, but FYI. All right, does that make sense? We tried to really talk through these strategies to work on each of these problems, and I hope that made sense to you. Any questions? I won't stop sharing yet, but you guys are free to go if you want, and I'll make sure this is posted as soon as it's ready. It's been processed on the Zoom side.
Thank you.
You bet. Have a good one.
Thank you. Homework
you bet. I can try to answer. I haven't thought much about the homework since I set it up. So.
Yeah, I'm just a little confused with the written homework, number 2.
So part 3.
It says part 2. Sorry.
Oh, no, you are okay. You are on part 2. Okay, I thought you meant the second written problem. Sorry, gotcha.
Yeah, so the first written problem, part 2 of the homework overall.
Okay. Yep. Give me a second to pull that up. Save that. Okay. All right. Homework 6, part 2. Okay. Okay. So not unlike what we did today, right? But a little different because now we have this free jet thing, right?
Right. So I'm having like too many things go to 0 now, so I feel like I'm doing something wrong.
Okay.
Because it looks like they're at the same height. So Z1 equals Z2.
Yep, I would call that. Yep, that makes sense.
And if it's a free jet, then that means that P2 is also equal to 0.
Yeah, let's see. So what is pushing up that 0.37 meters of water? That's got to be the velocity and pressure there, but I can see where if you make your stagnation velocity equal to 0 on both of those, you end up, what? You're just looking for H? Oh, H on the first one. Okay. So you're just basically looking for the pressure head back at, yep. Okay.
So yeah, it's just like if both of those are like stagnation tubes, then like V1 and V2, if you put like 1 and 2 right in front of the tubes, then those are both 0 as well.
Yeah.
And so like, is H just 3.7 then? You set P1 equal to P2, and so the H is the same? Or...
Yeah, let's see. So the 0.37 is going to represent, actually, if we go back to the notes from today, or from Thursday, either way. Oops. I had already closed them. I'm just reopening them. Okay, so that height H is equal to P. Sorry, let me share my screen with you. Where the heck did somewhere in here? I know Zoom is still working, right? Okay, there it is. All right, so share screen and this guy. Okay, so remember that this H on the right-hand end of the system over here, remember this is our actual setup, right? So this was going back and saying what's going on at 1. And when you do that, H is equal to the pressure head at 1 plus the velocity head at 1, okay? So what you're really getting is from that 0.37 is the, sorry, I'm just pulling it back up, is the those two heads back where H is being measured.
So for your picture, do you have 2 stagnation tubes, or is one of them like?
Yeah, in the homework, it's 2 stagnation tubes.
Okay.
Yes. Yeah.
So is the velocity 0 at both of the stagnation tubes?
It is, but the water's still flowing around it, right?
Yeah.
So you can't apply Bernoulli right at the front of that stagnation tube on the left one. Okay. That's the key here. Yeah, it's a little bit tricky in that way. If you do that, then you'll end up. Let's see, how would that work?
Yeah, so I did that for both of them, and then I just everything kind of went to 0, so the heights were equal.
Yeah, so if we instead look at what's going on in the flow, you would have P1 plus gamma being plus V1 squared over 2G. So these two heads add up to 0.37. But what happened with the that was if we kept the same smaller diameter, right? So what you have to do is think, oh, now what happens if I change my diameter to 0.08 instead of 0.05? So in other words, that 0.37 is giving you the velocity head if one, sorry, let me change my share with you so I can write on or point out something on the, oh goodness sakes, it's on the second slide, the second screen, of course. Not where I want it. Okay, there it is. All right, new share to do this thing. Okay, so now, so think of this 0.37 working from a point number 1 that's right here.
Okay.
Okay, so what that means then is that you can figure out a velocity because with this total, let me think about that for a second. You've got pressure head plus velocity head here, but you should be able to figure out a velocity. It might have to be in terms of this other Q back here, and then figuring out that velocity. So you'll have 2 equations, I think, and 2 unknowns to solve.
Okay.
Does that help you a little bit?
I think so. So I should be doing like the Q equals the volume times the area, and then set those equal to each other.
Velocity times the area.
Yeah, sorry.
Yeah.
Velocity times the area.
Yep.
Okay.
Both locations.
Yeah.
Strikes me, and perhaps I'm just confused, but it strikes me that we don't know the area for the second static.
Well, this is 0.05.
Before it leaves the tube, but that static nose in free air.
Yeah, but you don't need to know this diameter because the velocity that this is showing something from this rise for the velocity head, you're going to assume that's the same velocity as is in this part of the pipe. Does that make sense?
Right, but ideally we'd be subtracting that out of the full diameter, right? But even if we say it's so small that it doesn't matter, we're still looking at a divergent free jet, right?
Yeah, so we're ignoring the loss.